So welcome back. So we're now going to be moving on to the third section of this particular FAQ video. So the final section is to talk a little bit about oligopoly. Okay, so oligopoly is a less extreme form and it kind of falls in between. It's sort of basically, you got this scenario where there are a few dominant firms and they basically serve the majority of the market. So there's lots of examples of these, and I think that this is probably one of the most interesting topics of Micro 1. So the idea here is that there's only a handful of firms, typically, for example, the banking industry in Australia, and they basically serve a very large proportion of the market. Again, examples would then include the big four banks in Australia, the big four professional firms in Australia, that is Deloitte, PwC, EY, and KPMG. You could argue that even things like Coles and Woolworths is an oligopoly, right? Coles, Woolworths, IGA, the supermarket industry. You could argue perhaps the department store industry, right? Coles, not Coles, Myers and David Jones, although that's a bit of a dying industry. But there are lots of examples of these. Even in China, the big four banks in China, in the United States, you have, again, the few large, very big banks in America. Like, for example, JP Morgan, you have, for example, Citicorp, Wells Fargo, etc., etc., etc. Okay, so these are things that you're probably most familiar with. And the key thing here is that because these firms are so big, right, the impact of the decision made by one particular player, let's say CBA, will definitely affect that of NAB and Westpac, right? So the question then becomes, well, how do we kind of capture these market interactions? Is there a tool that we can actually use to analyze this? And the answer is, of course, yes. And what is that tool? That tool is game theory. Okay, so for those that have seen A Beautiful Mind, it's a fairly old movie now. It was a brilliant movie. It chronicles the life of John Forbes Nash, considered the founder of one of the founders of game theory, or at least he sort of popularized it. So basically, game theory is the tool that we then use to analyze oligopolies, because with game theory, it allows us to analyze how the impact of one firm's decision or one player's decision affects another. And the best way to show this is to basically do a very quick intro on game theory and to highlight each of these aspects. So let's talk a little bit about game theory. Okay. Effectively, there are four elements to a game. You have the player. Okay. What else would you have? You would definitely have the payoffs. Okay. What else? Well, strategy. What else? Well, timing. Some people tend to couple these together, and definitely for this course, timing is a little bit more, is not really emphasized as much, because typically the games that we will consider here are what we call one shot simultaneous move games. So in other words, everyone only plays this game once and they all move together. Okay, so one shot, they play it once, simultaneous move, everyone moves together. Okay, and hopefully now that we've kind of mentioned this, the game matrix should then begin to make a little bit more sense. Okay, so let's draw a matrix just to kind of highlight conceptually what we're doing. Okay, so we have the players. We call this player 1, and we have player 2. Okay, so let's call this 3, 4, 2, 7, 1, 1, 0, 5, 9. Okay. And the strategies, top, bottom, left, right. Okay. So we have all of the elements of the game, the players, the payoffs, okay, where usually the first number denotes the row player and the second denotes the column player, okay, and we have the strategies, okay, left, right, and top, bottom. The timing, one shot simultaneous move, okay. So with this, okay, you should begin to notice that, well, depending on what player 1 plays, you can immediately see that the payoff to player 2 kind of then changes, doesn't it? Right? So if he plays top, the payoff changes. If player 1 plays bottom, again, the payoff changes. And this captures the fact that the impact of the decision made by player 1 will affect player 2. Same thing if player 2 actually moves. Again, it affects, as you can see, the payoffs to player 1. And this is exactly the characteristics that we need to analyze oligopolies. Okay, so let's talk a little bit more about this. Okay, so how should player 1 move? Okay, so the first thing that you guys probably may have come across is this idea of a dominant strategy. Okay, and what is a dominant strategy? A dominant strategy is one which a dominant strategy is the strategy played if and only if it always results in the best outcome. So another way to think about it is that if, for example, player 1 always plays top, and regardless of whether player 2 plays left or right, top will always give him a better payoff than bottom, regardless of what left and right is. Okay, that's a sort of a conversational way of putting it, but you can find the exact definition in the textbook. So with that in mind, is there a dominant strategy here? Let's consider player 1. Well, if left is played, what would player 1 want to play? Well, he would want to play top. If right is played, what would player 1 want to play? Of course, bottom. So, of course, two different strategies. We don't have a dominant strategy. How about for player 2? If top is played, then what would player 2 want to do? Well, he would want to play right because, 7 is greater than 4. What about bottom? Well, if bottom is played, again, 9 is greater than 0. So, indeed, player 2 has a dominant strategy, which is right, isn't it? Okay. So you're going to say that, okay, how do we then think about, well, is there a point that both of these players will converge to? And the short answer is, again, yes. And that point is what we call the Nash equilibrium. Equilibrium. And what's a Nash equilibrium? A Nash equilibrium is a point where there is no incentive for you to deviate. Okay, so if we were to look at this, we would then say that, okay, is top left a Nash equilibrium? Well, how about player 1? Would he want to deviate? Well, let's see. 3 is greater than 1? No. Is 4? How about 4? How about player 2? Well, he would want to deviate to right, so this cannot be a Nash equilibrium. Let's consider top right. If it's top right, then again, is there incentive for anyone to deviate? Well, indeed there is, because for player 2, he's better off playing bottom now, so that can't be a Nash equilibrium. How about bottom left? Is that a Nash equilibrium? Again, in this case, he would want to, player 2 would want to deviate to right, player 2 would want to deviate to left, so definitely not a Nash. How about bottom right? Bottom right, is there any incentive for anyone to deviate? Well, would the second player want to deviate? Well, no, 0 is worse than 9, isn't it? Okay, how about for player 1? Well, 5 versus 2. 5 is better than 2, so there's no incentive for him to deviate. So this is your Nash equilibrium. Another way that you can solve for this is through what we call best responses. Exactly the same thing, and the intuition is if you choose your best response, naturally there's no incentive for you to deviate. And how do we do this? So the first thing we say is let's put ourselves in the shoes of player 1. If player 2 chooses left, what would I want to choose? I would want to choose top. If player 2 chooses right, what would I want to choose? Well, I would choose bottom. If now I'm player 2, player 1 plays top, what would I want to play? I'd play right. Not surprising because remember 2 was the dominant strategy. How about bottom? Right. So again, note that there are 2 underlines here or 2 ticks. Again, that would immediately tell you that that is your Nash equilibrium. Okay. So that is sort of the basics of game theory. Of course, you can kind of use this tool to analyze different types of games, like for example, the prisoner's dilemma. And it's from that particular game that you'll begin to understand why, by assuming that you have an entry barrier and there's only 2 players in this market, it is actually possible that if you left them to do their own thing, they would actually arrive at an inefficient outcome. Okay, definitely possible. And this is basically the point that we're making. The moment you break one of the assumptions in perfect competition, it is indeed possible for you to arrive at an inefficient outcome if you leave the market to its own devices. Okay, that's a key point. So the other thing is, consider this game. And this is a game which I kind of mentioned in a collaborate session. Okay, so top, bottom, left, 2, and 1. So we have -1, 1. So we have 1, -1, -1, 1, and 1, -1. What's the Nash equilibrium of this game? Is this a Nash? No, because player 1 will want to deviate. Cool. How about this one? Is this a Nash? No, because again, player 1 will want to deviate. Okay. Is this a Nash? No, because player 2 will want to deviate. How about bottom right? Is that a Nash? No, because again, player 2 will want to deviate. Oh no, player 1 will want to deviate. Okay. So you're going to say to me, hey, there's no Nash here. And I'm going to say to you, like I did in a collaborate session, are you going to say that John Forbes' Nash is wrong? Because John Nash basically said that for every finite game, there is always a Nash equilibrium. This is indeed a finite game. So this was a question I posed to a couple of students. So what exactly is the Nash here? And the hint which I basically gave them was, well, let's generalize this a bit and introduce a little bit of statistics and probabilities into it. If we say that we're going to play L with probability P and 1 minus P, and this thing with probability Q and 1 minus Q, is it then possible for you to then identify what the appropriate P's and Q's are? Because if you think about it, when we say that we will play L, that's like saying P is equal to 1. If we say that player 1 is going to play T, that's like saying that Q is equal to 1. So now we've basically generalized it. So once you generalize it this way, you can indeed find a Nash. Okay. And of course, for those that are attached to calculus, you can immediately identify how you do this. You can obviously find what the best response is for each of these players and then solve them simultaneously using calculus as well. That way, that is what we call a mixed strategy. Okay, and this is briefly covered in your textbook in one of the questions. I think it was the last question in that particular chapter. And for this particular game, what you're going to find is that the probability, the mixed strategy, is 0.5, 0.5. In other words, they're going to mix between left and right, and player one is going to mix between top and bottom. Okay, so just be aware that this is definitely in your textbook. It is a little bit tricky. It requires a little bit more thinking with regards to probabilities. But again, it might be a bit of a nice exercise for you to just give it a go, because it will definitely test your knowledge on how well you understand best responses, and of course what these things actually mean. So that's one of the key things which I really wanted to get through to you guys today, because it seems that you guys kind of understand the tools and everything, but are lacking a little bit in terms of the overarching picture, and I thought I'd do that. So anyway, this is basically going to be the second last video. There will be one more video coming out next week, hopefully next week, assuming everyone's on board. And that will focus more on externalities and public goods. So with that in mind, all the very best, and I'll see you all online very, very soon. Take care.